Good day, everyone. So diagonal matrices is the topic today. V is a vector 1, 1. This is an example vector. So this is a 2D space. This has two components. A is a diagonal matrix. The primary diagonal, the main diagonal has non-zero cell values. The secondary or the other diagonal has zeros. So the diagonal matrix has an effect of stretching the x direction. We are doing a multiplication operation with the matrix, and that has an effect of transforming, in this case, stretching the vector along the x direction. Okay, in this second visual, we have a circle as well as the vector 1, 1. The circle represents all the vectors with a length of 1. So the diagonal matrix A is exactly the same. We are actually using the same diagonal matrix to transform this time the circle, and we are seeing that it actually has transformed into an ellipse with the major axis along the x direction. It had an effect of stretching along the x direction. In the third visual here, the vector is the same. It is 1, 1. The diagonal matrix is also the same. The operation and the result 2, 1 is also the same. The visual, however, is showing the coordinate grid getting compressed along the x direction. So the math is exactly the same. This is a visual, difference in the way in which we are visualizing this. This is convenient in some cases. When we look at rotation matrices and symmetric matrices, we'll be able to appreciate how this helps us more. We are taking the same vector 1, 1, but this time there are two matrices A1 and A2. A1 is the same matrix with lambda 1, 2, which was stretching along the x direction. A2 has a lambda 2, 3, which has an effect of stretching along the y direction. We are doing these steps separately first. A1 first, followed by A2. This got us 2, 3 as the vector. And the diagonal matrices are commutative. So it is okay to apply use A2 to transform the vector first, that is scale along the y direction first, and then actually scale along the x direction next. So also actually we can do the matrix multiplication of A1 and A2 and get an A3, which is having lambda 1 as 2 and lambda 3 as 3, and do the transformation using the A3 matrix. All these three are equivalent. Diagonal matrices are commutative, which means that A1 A2 is equal to A2 A1. So we are taking the same vector 1, 1, but this time basically we are seeing a rotation matrix which has the primary diagonal and sin theta and minus sin theta terms on the secondary diagonal. So this is easy to derive this rotation matrix by actually performing the rotation along a circle and projecting to the x component and the y component and doing the derivation. So it's straightforward to get the matrix that we have on the scene. There are multiple ways to do that also. Using such a matrix has an effect of doing the rotation of the vector. We have the same vector here, but this time actually the coordinate grid is rotating in the clockwise direction. The math is exactly the same. The vector is kept in one place and the coordinate grid is rotated. So this is a useful tool to have at our disposal, for visualization as well as for understanding. Having the choice of either rotating the coordinate grid or the vector can come handy. Okay, in this case, actually, we have two rotation matrices, R of alpha and R of minus beta. So we are doing matrix composition. That is actually we are, multiplying both these rotation matrices and expanding that. So basically what we are able to see is that the angles added up, that is 60 minus 30. We are, we started with alpha and minus beta, and when we do that matrix multiplication operation, we are able to see that the angles added up. The resultant angle became 60 minus 30. But basically to contrast against the diagonal matrices, rotation matrices are not commutative. In 2D space, there is only one rotation angle possible where commutativity applies for two-dimensional 2x2 matrices, but for higher dimensional matrices, rotations are not commutative and the order matters. Okay, let's look at a symmetric matrix. So A is a symmetric matrix. That is actually the transpose of the matrix is equal to the matrix itself. So a transpose of a matrix is taken by flipping over the rows and the columns. In this particular example, if we take row 1, if we flip it over, the column 1 is exactly the same. 2, 1 are the cell values that are there in the row 1 as well as in the column 1. And the same thing for the row 2 also. Row 2, if we flip it over, we see exactly the same cell values in column 2 as well. So A is such a matrix is a symmetric matrix. So the nice thing about symmetric matrices is that they can be composed using rotations and scaling. So let's look at the visual and actually understand this a little bit more. So we are taking a vector. So this vector actually has the components directions as E1 and E2. First, actually the R transpose, is the first operation that we do. X dash is R transpose X. That is actually, we have actually rotated the coordinate grid here. So the next operation that we do is lambda. Lambda is a diagonal matrix. The R lambda R transpose is what we have here. First we did R transpose. Now we are doing lambda on that. So lambda is a diagonal matrix which has an effect of stretching, but the interesting part is that now the stretching is along the E1 dash direction, which is the rotated direction. So after doing this operation, let us actually do the R matrix, use the R matrix, which actually rotates the coordinate grid back to where it was. So we are now once again back to E1, E2 as the coordinate basis. So symmetric matrices can be, organized as rotation, scaling, and rotate back. So that is the main takeaway here.